Welcome to our very first lecture on time series analysis. Today we are going to explore what time series data actually is and why it is so incredibly important in the world of statistics. Whether you are tracking the stock market, predicting the weather, or monitoring a patient's heart rate, time series data is everywhere. Let us dive in and build our understanding from the ground up. To start, let us think about a simple everyday example. Imagine you are trying to lose weight. So you step on a scale every single morning and write down the number. After a month, you have a list of 30 numbers. But these are not just random numbers, they are tied to specific days. This simple act of recording a measurement in the order that time passes creates what we call a time series. The exact order is critical. If you mix up the dates, the story of your weight loss disappears completely. That is why time is the most important character in this mathematical story. Now that we understand the basic idea, let us look at how we write this formally in statistics. The formula you see here represents a collection of measurements taken over a specific period. The curly braces indicate we are looking at a complete set of data points. Inside, the capital letter Y sub t represents the actual value we are measuring at a specific moment, like daily temperature. The small letter t is our time index, which tells us exactly where in the timeline our measurement belongs. Finally, the capital letter T represents the entire time domain we are observing. As the time index t increases, we move forward into the future, observing new values of y. Building on our formal definition, we need to understand that time series data can be collected in two different ways. The first is a discrete time series, where observations are recorded at specific, separate, and equally spaced intervals. Think of checking your bank account balance exactly once a day at midnight. You only get one number per day. On the other hand, a continuous time series is recorded constantly, without any breaks. A perfect example is a heart rate monitor in a hospital, recording every fraction of a second. Even though the real world often happens continuously, we usually convert continuous data into discrete snapshots so computers can easily analyze it. Another important distinction we must make depends on how many different things we are measuring at the exact same time. If we are only tracking a single variable, like the daily closing price of a specific stock, we call it a univariate time series. The prefix uni means one. However, if we track multiple variables simultaneously, it becomes a multivariate time series. For example, if a weather station records temperature, humidity, and wind speed every hour, these three separate measurements are tied together by the exact same hourly timestamps. We study them together because variables often interact with each other over time, like wind speed affecting the temperature. Before we do any complex math with our data, the very first step in analyzing a time series is to draw a picture of it. We call this a visual time series plot. It is simply a line graph showing how our data changes over time. Because time moves forward independently, we always place time on the horizontal axis or the x-axis. The variable we are actually measuring goes on the vertical axis or the y-axis. By connecting our data points with straight lines, our eyes can instantly spot trends, like whether a business is growing or shrinking. Let us look at a concrete visual example of a coffee shop's daily revenue to see how this works in practice. Looking at the graph on your screen, you can immediately see the story the data is telling. The horizontal axis tracks the days, from day 1 to day 5. The vertical axis tracks the money earned in dollars. Notice how the data points are connected by lines? Even though the revenue dipped slightly on day 3, dropping to $160, the overall visual trend shows that the coffee shop is making more money as the week progresses. This visual intuition guides all the mathematical analysis that follows. Now that we have visualized the coffee shop data, let us formally write it out using the mathematical notation we learned earlier. We are given a 5-day record of revenues and we need to represent this univariate, discrete time series mathematically. We will assign the day number to our time index t and the revenue to our variable y sub t. For the very first day, our time index t equals 1. The recorded value is exactly 150, so y sub 1 equals 150. For the second day, the time index moves forward to 2. The revenue increased, so y sub 2 is recorded as $180. Continuing with our sequence, on the third day, our time index becomes 3. The revenue dropped slightly compared to the second day, so we record y sub 3 as being equal to $160. Moving to the fourth day, we set our time index to 4. The revenue bounced back up significantly, so we record this new observation as y sub 4 equal to $210. Finally, on the fifth day, we reach the end of our current dataset. The revenue reached its absolute peak for the week. This gives us a final data point, y sub 5, which is equal to $250. This step-by-step breakdown shows exactly how real-world events translate into a mathematical sequence. We have successfully modeled a single variable. But what happens when we track two different variables at the exact same time? We cannot just use a single variable like y sub t anymore. Instead, we use a mathematical vector to organize our data. A vector is just a way to group multiple numbers together in a vertical list. In this formula, v sub t represents the combined multivariate observation at any given time t. The large square brackets group our two distinct variables together into one single object. The top variable, E sub t, represents the temperature, while the bottom variable, H sub t, represents the humidity. As time moves forward, both variables are recorded simultaneously as a single package of data. Let us apply this vector formula to a slightly more complex scenario involving a digital weather station. We are given that at the very first hour, the temperature was 22 degrees Celsius and the humidity was 60%. We want to represent this data mathematically. By substituting our specific numerical values for the first hour, where t equals 1, we get our final mathematical representation. The top number in the vector, 22, is the measured temperature. The bottom number, 60, is the measured humidity percentage. This simple grouping shows how multivariate time series keep different types of measurements perfectly aligned in time, allowing us to study their relationship. Now that we know how to write and visualize time series data, we must ask, why does this matter? Understanding time series data is absolutely crucial because the real world operates on timelines. Businesses rely heavily on time series analysis to forecast future sales, ensuring they have enough inventory on the shelves before a busy holiday season. Meteorologists use it to predict tomorrow's weather by looking at the sequence of past climate data. In the medical field, doctors analyze continuous time series data from electrocardiograms to detect irregular heartbeats before they become fatal. Without the ability to analyze data in the specific order it was recorded, we would be completely blind to trends and future predictions. Let us quickly recap the key takeaways from today's lecture. First, a time series is simply a sequence of data points recorded in chronological order. We learned that this data can be discrete, like daily bank balances, or continuous, like a heart rate monitor. It can also be univariate, tracking one thing, or multivariate, tracking several things at once. Regardless of the type, the defining feature is that time is the most critical variable. By plotting this data visually and representing it mathematically, we build the foundation needed to uncover hidden patterns and forecast future events. You now have a solid understanding of what time series data is. Great job today.